Since the year 2000, Boeing alone has handed over more than 1,800 wide-body jets to airlines around the world. Russia, in that same stretch of time, has managed 16. Say that number out loud and it sounds like a punchline, like a country that simply gave up on building big airplanes. The obvious story is sanctions, political isolation, a shrinking industrial base, and sure, all of that is real. But talk to the engineers who actually work inside Russia's aviation program, and you'll hear a different story. They'll tell you the gap was never really about airframes, rivets, or wings. It came down to one single part, a part that only a tin-wide handful of nations on this planet have ever fully figured out how to build. And that raises a strange question. Why is Russia now pouring money, time, and political capital into an engine that, as of today, still doesn't officially exist in a finished form? Why bet the future on a piece of hardware that isn't even attached to a plane anyone particularly wants to fly? Stick around, because by the end of this, you'll understand exactly what's going on and why the rest of the aerospace world is quietly watching. If big engines, forgotten airplanes, and industrial power struggles are your thing, subscribe, because this channel lives right here. At first glance, the Aviation IL-96-400M looks like exactly what everyone assumes it is. An old Soviet design, pulled out of storage, dusted off, and relaunched with a fresh coat of paint. A vanity project. A nostalgia trip. Maybe just an expensive way of keeping a few factory lights on a little longer. And honestly, that reaction makes sense. Seeing a 4-engine Russian wide-body reappear in a world that now runs on the Boeing 787 and the Airbus A350 feels almost like watching a rotary phone show up at a tech conference. It feels like the rest of the industry moved on, and this particular airplane simply didn't get the memo. But here's what almost everybody watching from the outside gets wrong. The real obstacle was never Russian engineering talent. It wasn't ambition, and it definitely wasn't the airframe itself. The real obstacle was hanging underneath the wings the entire time. Rewind to the 1980s for a second. Back then, strapping 4 engines onto a long-haul jet wasn't just normal, it was the standard for anything serious. 4 engines meant power. It meant prestige. Nobody in an airline boardroom looked at a 4-engine jet and thought, that's inefficient. They thought, that's a serious airplane. Then the industry flipped almost overnight. The Boeing 777 proved that you could send a massive jet across an ocean on just 2 engines and do it safely, reliably, and profitably. Then the 787 landed, followed by the A350, and long-haul economics got rewritten from scratch. 4 engines stopped being a symbol of strength. They became a red flag on a spreadsheet. It's a bit like what happened to the V8 engine in the car world. People loved the sound, the size, the raw feeling of power under the hood. Then, smaller turbocharged engines showed up and delivered nearly the same performance while sipping a fraction of the fuel, and buyers slowly drifted away from big displacement toward efficiency. Aviation went through its own version of that shift, except the stakes were measured in millions of dollars per aircraft per year. And here's the thing about airlines that people outside the industry often miss. Airlines don't fall in love with airplanes. They fall in love with spreadsheets, fuel burn, maintenance intervals, turnaround time, profit per seat mile. That's the entire romance. It's why the A380 is disappearing from fleets years ahead of schedule. It's why the original 747 passenger variant is basically extinct now, and why the A340 barely exists outside of cargo conversions and museum displays. None of those were bad airplanes. Some of them were engineering marvels people genuinely adored. But loving an airplane and justifying it financially are 2 completely different things, and the math simply stopped adding up. It's worth pausing on the IL-96 itself for a moment, because the airplane has a longer and stranger history than most people realize. The original IL-96-300 first flew back in 1988, right at the tail end of the Soviet era, and it was genuinely a serious piece of engineering for its time. Supercritical wing design, a fly-by-wire control system that was actually ahead of a lot of Western airliners in certain respects, and a cabin that could carry passengers comfortably across intercontinental distances. It even briefly served as a presidential aircraft, and a small fleet has quietly carried senior Russian officials for decades. But commercially, it never really took off outside of Russia. A handful of airlines operated it, mostly domestic carriers with limited alternatives, and production numbers stayed embarrassingly low compared to anything Boeing or Airbus was rolling out during the same stretch of decades. By the 2010s, the jet had essentially become a footnote, a symbol of what Soviet and post-Soviet aerospace ambition looked like without the industrial scale to back it up. Then came 2022, and everything about that footnote suddenly mattered again. With Western aircraft leasing arrangements collapsing, spare parts embargoes tightening, and new Boeing and Airbus deliveries essentially cut off overnight, Russian officials went looking for anything in the country's own industrial history that could plausibly be revived. The Il-96 line was still technically active, if barely, and the tooling at the Voronezh Aircraft Production Association hadn't been fully dismantled. So the modernized 400M variant, which had actually been floating around in smaller numbers since the mid-2010s as a cargo and VIP transport, got pulled into the spotlight as a potential answer to the sudden hole in Russia's long-haul passenger fleet. Officials talked about ramping production up to multiple aircraft per year. Reality so far has looked considerably more modest than that, with deliveries trickling out one or two at a time rather than the fleet scale numbers originally floated. Now, here's where it gets interesting for Russia specifically. The original Il-96 already had a functioning engine, the PS-90A. It's a tough, dependable, thoroughly Soviet-flavored piece of engineering, the kind of motor that just keeps turning over no matter what conditions you throw at it. But reliability alone can't rescue a 4-engine airplane in a 2-engine world. You still need 4 sets of maintenance schedules, 4 sets of inspections, 4 fuel-hungry power plants, doing the job that modern aircraft now do with 2. Every additional engine is another line item quietly terrifying an airline's finance department. So naturally, you'd think the fix is obvious, right? Just pull the 4 older engines off, bolt on 2 modern high-thrust engines instead, and suddenly you've got a leaner, meaner, far more competitive aircraft. On paper, it sounds almost too simple. Keep the airframe, have the engine count, improve the fuel economy, improve the range, and call it a day. Except there was one enormous problem standing in the way. Russia didn't actually have an engine like that. Not the thrust class, not the fuel efficiency, not the exotic heat-resistant materials, not the generation of turbofan technology that powers a Dreamliner or an A350. And the moment you realize that, this stops being a story about a slightly outdated airplane. It becomes a story about a country trying to rebuild, from almost nothing, one of the single hardest technologies in the entire aerospace industry. It's also worth understanding just how rare it is for any country to successfully build a large civil turbofan from the ground up in the first place, because this is not a club with an open-door policy. The United States has GE, Pratt & Whitney, and a joint venture stake in CFM International through the decades. The United Kingdom has Rolls-Royce, one of the last truly independent engine makers left standing outside American ownership. France, through Safran, holds the other half of CFM. And that, historically, has more or less been the entire list of nations capable of independently designing, certifying, and mass-producing large high-bypass turbofans for commercial aircraft. Japan contributes major components through partnerships, but has never fielded a fully domestic large turbofan of its own. Germany's MTU is a critical partner on multiple programs, but again operates within international consortiums rather than as a standalone prime. China, despite pouring enormous state resources into its own engine programs for years, is still working to close the gap on its smaller CJ1000 before it can even seriously approach the thrust class the PD-35 is targeting. That's the real competitive landscape Russia is trying to force its way into, and it explains why Western aerospace analysts didn't just shrug this program off as another underfunded Cold War leftover trying to relive past glory. That missing piece has a name. It's called the PD-35. And this engine might genuinely matter more to Russia's future than the airplane it was originally imagined for. Here's the number that should stop you in your tracks: 35 tons of thrust. That figure alone puts this program in direct competition with GE's monstrous GE9X, the engine strapped underneath Boeing's 777X, an engine capable of producing close to 50 tons of force at its upper limit. It sits in the same weight class as the Rolls-Royce Trent XWB that powers the Airbus A350. These are not ordinary engines. These are the power plants that move the largest passenger jets on Earth across the longest routes with the heaviest payloads. This is, without exaggeration, the single hardest neighborhood in all of aerospace to break into. Here's why. Inside an engine like this, the turbine inlet temperature can climb past 1500 degrees Celsius. Picture that for a moment. That is hotter than flowing lava. And in that furnace of heat, turbine blades are spinning at thousands of revolutions per minute in conditions that would turn ordinary metal into a puddle within minutes. The materials inside these engines don't just need to survive that environment. They need to perform, precisely and repeatedly, at the absolute outer edge of what modern materials science allows. Historically, only a small circle of organizations on the planet has ever truly mastered that challenge. GE Aviation, Rolls-Royce, CFM International, and increasingly backed by enormous state investment, China's aerospace industry. Russia wants a seat at that table too, and after 2022, wanting it stopped being optional. Before the sanctions hit, Russian carriers were flying hundreds of Western-built aircraft. Boeing 737s, Airbus A320s, Western engines under the wings, Western avionics in the cockpit, Western everything, essentially, from nose to tail. When the sanctions landed, it wasn't just that new jet deliveries got frozen, it exposed something much deeper and far more uncomfortable. That dependency on Western aerospace technology wasn't some surface-level inconvenience you could simply route around. It was the foundation the entire Russian commercial aviation system had been quietly built on top of. Suddenly, replacing that foundation wasn't a talking point in a strategy meeting. It was an emergency. So where does the PD-35 actually stand right now? Development officially kicked off back in 2017 under Russia's United Engine Corporation, built around a shared gas generator core borrowed from the smaller PD-14 engine, which itself is already flying and undergoing certification testing. A technology demonstrator for the PD-35 was assembled in 2023 and began ground testing the following year at an outdoor test facility near Perm. And here's the part that genuinely surprised a lot of Western analysts who had written this program off entirely. During those ground runs, including repeated tests at full takeoff thrust, the demonstrator actually hit its 35-ton target. Engineers logged more than 50 separate engine starts, validated over 20 new technical solutions, and gathered real data on how the engine handles thermal stress, mechanical load, and long-term durability of its bearings and composite parts. The fan itself spans roughly 3.1 meters across, and through the aggressive use of composite materials, the design team has already trimmed more than 600 kilograms of weight off the engine, with over 2,000 components now produced using additive manufacturing, essentially industrial-grade three-dimensional printing, built layer by layer rather than machined from a solid block. None of that means the engine is finished. Far from it. Russia is now constructing a dedicated purpose-built outdoor test stand in the Perm region, specifically for the PD-35, a facility unlike anything else currently operating in the country, with construction beginning in 2026 and wrapping up the year after. The head of Rostec has publicly stated he expects a type certificate within 2 to 3 years from that point, which, if everything goes smoothly, would put certification somewhere around the end of this decade. For comparison, GE's own GE9X took over a decade to go from initial concept to full certification, and that was with the entire industrial weight of GE Aviation behind it. Billions of dollars, thousands of engineers, generations of accumulated institutional knowledge that simply cannot be conjured up overnight. Russia is now attempting something in the same ballpark, under active sanctions, with a compressed industrial base and in a fraction of the time GE had available. That's not impossible. History has examples of nations closing technological gaps faster than anyone expected, but by any honest measure, it is extraordinarily difficult. And yet, the program keeps moving. It's funded. It's producing real hardware, not just press releases. The people running it appear to fully understand exactly how high the stakes are. Here's where the story takes a turn that most casual observers completely miss. The PD-35 was never designed purely with the IL-96 in mind. And the IL-96-400M isn't just sitting on a runway somewhere, patiently waiting for its future engine to show up. These two programs are running on a piece of strategic logic that almost nobody outside Russia's aerospace establishment has fully connected together. And if you're finding this as fascinating as I do, go ahead and hit like right now. It genuinely helps videos like this reach more people who care about this stuff. So let's actually answer the question everybody watching this is probably asking by now. If this engine program is supposedly this important to Russia's national strategy, why are so few IL-96-400M arms actually being built? Why isn't there a queue of airlines lining up to order one? Why does an aircraft with this much stated symbolic weight have essentially zero real commercial traction? The answer is that this was never really meant to be a commercial success story in the traditional sense. The IL-96-400M likely was never designed to win against the 787 or the A350 in a straight fight for airline contracts. It was built to preserve something that, once lost, is almost impossible to rebuild from scratch. And that's the actual engineering capability to design, build, and certify a wide-body aircraft at all. Think of it like a muscle. Stop using it, and it doesn't just weaken, it wastes away entirely. And in aerospace engineering specifically, that kind of atrophy doesn't just mean falling behind, it means near total extinction of the capability. Engineering teams disperse to other industries. Decades of accumulated institutional knowledge, the kind that lives in people's heads and never quite makes it fully into a manual, walks straight out the door and never comes back. Supplier networks dry up and shut down, and when a country tries to restart a program like this years later, it isn't picking up where it left off. It's starting from something close to zero. GE Aviation understood exactly this dynamic when they were developing the GE9X, the very same thrust class the PD-35 is now chasing. They didn't just run that engine in a stationary test cell and call the job done. They physically mounted early GE9X prototypes onto a modified Boeing 747, specifically so they could gather real flight data in actual airborne conditions. That 747 was never going to carry the GE9X into commercial passenger service. That was never the point. It was simply the fastest, most controlled way to stress test a next-generation engine on a platform GE already had full command over. Russia appears to be running that exact same playbook right now, just with a different aircraft standing in as the test mule. The IL-96-400M keeps the Voronezh aircraft plant operational and busy. It gives engineers a real, physical, certifiable airplane to build, iterate on, and troubleshoot, rather than a purely theoretical concept sitting in a design document. It keeps the wide-body specific tooling running, keeps the supply chain from fully collapsing, and keeps the institutional muscle memory alive that some future aircraft is eventually going to need. And that future aircraft, by pretty much every indication available, is almost certainly not going to be another 4-engine IL-96 variant. The real endgame, the thing this entire program appears to be quietly building toward, is a clean-sheet, next-generation twin-engine wide-body powered by a pair of PD-35s aiming to compete, at least on paper, in the same performance bracket currently occupied by the A350 and the 777X. So, no, the current Russian widebody was never truly designed to compete head-on with Western jets. It's the bridge. It's the thing you build specifically so that when the moment finally arrives to build the real answer, you're still capable of doing it. But here's the part that complicates everything, and it's worth sitting with for a second. Building a bridge is one challenge. Actually crossing it on schedule before the rest of the world moves even further ahead is a completely different one. Even with the recent progress, the PD-35 remains years away, quite possibly the better part of a decade away, from genuinely competing with the GE99X or the Trent XWB at true commercial scale and volume. Those Western engines were built on top of decades of accumulated industrial evolution and billions upon billions of dollars in research infrastructure that took multiple generations of engineers to establish. Russia is trying to reconstruct meaningful pieces of that foundation under active sanctions, under serious financial pressure, and with a materially smaller talent pool to draw from. That is not a small ask by any stretch of the imagination. For a long stretch after 2022, plenty of Western analysts quietly assumed Russia had permanently lost the ability to compete in large commercial engine development altogether. The fact that the PD-35 program is not only still alive, but is putting real, verifiable hardware on a test stand and hitting its thrust targets is genuinely what caught a lot of those analysts off guard. There's also a quieter, more human side to this story that rarely makes it into the headlines. Rebuilding an engine program like this isn't only about metallurgy and test stands, it's about people. Russia's aerospace design bureaus went through a brutal talent drain in the 1990s and 2000s as engineers left for better paying work abroad or simply left the industry altogether once state funding dried up after the Soviet collapse. Rebuilding a pipeline of turbine specialists, material scientists, and combustion engineers capable of working at this level takes years of dedicated training, not just budget line items. Some of the specialists now leading pieces of the PD-35 program are reportedly veterans who cut their teeth on the PS-90 decades ago, while a younger generation is being trained up alongside them specifically so that knowledge doesn't disappear again the next time an economic downturn hits. That generational handoff is, in its own way, just as fragile and just as important as any single technical milestone on a test stand. And here's what turns this from a purely Russian story into something with much bigger global implications: China. For years, Russia and China were jointly developing the CR-929, a twin-aisle widebody explicitly designed to go head-to-head with the Dreamliner and the A350. The PD-35 was originally pitched as the Russian-supplied engine option for that exact aircraft. That partnership has hit serious, well-documented turbulence, and China has been increasingly exploring its own domestic alternatives instead of leaning on Russian propulsion technology. But think through what happens if the PD-35 program reaches genuine maturity, even partial maturity, in the next several years. At that point, you're no longer just talking about Aeroflot's fleet planning decisions. You're talking about the possibility of an engine family that could, in theory, plug into a market of over 1,400,000,000 people, in a country that has repeatedly and explicitly stated its intention to reduce its long-term dependence on Western aerospace suppliers. That's the real thing serious analysts are watching right now. Not how many IL-96 roll off the line this year, but whether a credible, functioning, non-Western wide-body engine ecosystem could realistically emerge sometime before the end of this decade or shortly after. Because if that actually happens, even partially, the entire calculus of the global aviation supply chain shifts in a way that ripples far beyond Russia's own borders. There's a broader pattern worth zooming out to see here, too. Every major aerospace power that matters today got there the same way, by refusing to let a temporary commercial failure kill a long-term strategic capability. The United States kept funding military engine programs through decades when commercial orders were thin, and that military investment quietly subsidized the research that eventually produced engines like the GE9X. Rolls-Royce survived a near bankruptcy in the 1970s that required a full government nationalization to keep its engineering base intact, precisely because the UK government judged that losing the capability entirely would be far more costly in the long run than propping it up through a rough patch. China is currently pouring what analysts estimate to be tens of billions of dollars into its own engine ecosystem over multiple 5-year plans, fully aware that commercial competitiveness might be a decade or more away, because the alternative is permanent dependence on foreign suppliers for a technology considered too strategically important to outsource. Viewed against that backdrop, Russia's approach with the IL-96 and the PD-35 doesn't look quite as eccentric as it first appears. It looks like a smaller, more resource-constrained version of a playbook every serious aerospace nation has run at some point in its history. The IL-96-400M was never really Russia's answer to the Dreamliner, and treating it like a failed competitor to Boeing and Airbus misses the entire point of why it exists. It's the machine quietly keeping the lights on inside Russia's wide-body industry, while the country builds the engine that might eventually make a genuine answer possible. There's one more wrinkle worth mentioning before we close this out, because it shapes just how much runway Russia actually has to get this right. The PD-35 isn't only being pitched as a civil engine anymore. Reporting has increasingly framed it as part of a broader family spanning roughly 24 to 50 tons of thrust, with variants explicitly discussed for future heavy military transport aircraft, as well as commercial wide-bodies. That dual-use framing matters, because it means the program isn't purely dependent on a fragile commercial business case to keep its funding alive. Military transport requirements tend to survive budget cycles that would otherwise kill a purely civilian program the moment passenger jet orders failed to materialize. In a strange way, tying the PD-35's future partly to defense logistics may end up being one of the more realistic paths to actually getting this engine across the finish line, even if the commercial widebody it was originally imagined for never sells in meaningful numbers. Whether the PD-35 actually arrives in time to matter on the global stage is a question that, honestly, even the engineers at Rostec probably can't answer with total confidence today. Is this ultimately going to be remembered as a genuine breakthrough that reshapes the balance of the aerospace industry? Or is it a technically impressive achievement that simply arrives a decade too late to change anything meaningful? Drop your take in the comments below, because on this particular question, even the actual experts studying this program don't fully agree with each other.